All right. So, I think that your quarter grade will post tomorrow online, your grade cards. So make sure you take a look at those, obviously. So we're gonna continue. Looks like things went pretty good on the Earth's layers, those important characteristics, where the layers are. Hold it, please. Thank you. Where you can, where you find those things. Usually a question that comes up is, well, we know that the inner core is the absolute hottest layer. Where does all that heat come from, right? We know that the heat that we feel comes from where? Like while we're here on the crust, where does the heat come from that we feel? Okay? The sun, right? Is the sun gonna warm up our inner core though? Does that make sense? Probably not. Haley's like, no, right? Not even close. So usually people ask, well, where does this come from? How did this happen? Why is it still hot? And so that's what we're gonna take a look at. So the temperature exceeds 11,000 degrees Fahrenheit, and that is actually hotter than the surface of the sun. And that's a little bit scary. As you think about it, we're like, okay, so we are standing on a planet that has a center that is hotter than the surface of the sun. And we're a lot closer to that center than we are our sun, right? But we're not feeling any heat coming up through there. So it's like, okay, that's a good thing, I guess. That heat is causing something, right? What are the currents that are moving because of the heat caused from the core? Those convection currents. Good. All right. So, about 1 billion years ago, within about 1 billion years of its formation, the Earth was kind of superheated, and there's 3 main sources that are kind of attributed to how our Earth got so hot, right? How our planet was so warm. The first one is called gravitational energy. Well, probably gonna have something to do with gravity, right? That's probably realistic. We're gonna also talk about the decay of radioactive material. Now, we're going to talk about radioactive decay a little bit when we talk about dating fossils in a couple units from now. And then again, we have a whole unit on this next year. So I'm going to introduce it, but it's not something that you're going to have to be like totally mastery of radioactive material or decay. Just kind of have a general understanding, and then we'll get into that more in depth next year. And then finally, friction. All right, so friction is a pretty easy concept. And so gravity, friction, pretty easy, and we'll kind of just touch on the surface of radioactive decay, what that means. Okay, so even though the core is only small, it's really only a small portion of our entire Earth, it's the heat source generated from these materials that are escaping very, very slowly into the upper layers, right? And so it's why the interior is able to kind of remain molten or melted, have that magma, which is like that internal lava that stays so hot. So we're going to look at each of these 3 sources. And again, you're not going to have to know like the in-depth details of them, but to identify what those 3 sources are, you're going to need to be able to do that. You're going to need to know the gravitational, radioactive decay, and friction all contribute to Earth's internal heat. All right, so the first one, gravitational energy. Well, as the Earth formed, small, solid bodies of rock get pulled together. Typically, things are going to get pulled to the center of the largest item. We know that that's going to have the greater gravitational pull. So everything is going to kind of be pulling to the center. Right? And when they collide, they are moving a lot of times very quickly, and they're able to kind of like fuse or stick together. And that gravitational energy caused the movement, or kinetic energy pulled them together, and some of that kinetic energy transfers into heat or thermal energy. Kinetic energy is energy of movement, right? And so as these things are moving, some of that kinetic energy is gonna transfer into heat energy. Okay, and again, some of this is a little bit, like, it's very simplified, and that's all you really need to know. You don't need to know, you know, anything too more in depth than that. Oh, one little clip for that little extra period. Interesting. All right, the other way that there is some heat being generated is through radioactive decay. And so the interior of the Earth is made of these radioactive isotopes. Radioactive isotopes are usually nuclei that are very large, meaning they have a bunch of protons and neutrons, and because they're so large, they have a hard time staying together. That nucleus isn't able to stay sticky enough to stay as one nucleus, and a lot of times it will split into two smaller nuclei. We call that process radioactive decay, right? Sometimes when that process happens, radiation is given off, and there's three different forms. One is not very dangerous at all, one can be a little, and then the third can be extremely dangerous. And so one of the kind of side products or side effects is that a bunch of heat energy is given off. When this nucleus splits into two smaller, a bunch of energy gets released, okay? And so a little bit of radiation, but a lot of heat energy. And so if that's happening inside the Earth, it's kind of, you know, being held in there, right? And so, again, for now, that's all you have to know. Decay doesn't mean like rotting, you know, leaves or rotting meat or something like that. When we say radioactive decay, we mean it's this nucleus is breaking apart. This big nucleus can't hold together, and it splits into two smaller ones, right? But the important part of that is that a big burst of heat energy is released. Right? And again, we're going to get into this a lot more when we get into radiometric dating, and then even more next year. We have a whole unit on it. So if you're kind of like, what, or I'd like to know more, hang tight, that time is coming. Yes?
If, like, the Earth is, like, hotter than the sun, why doesn't it just melt everything?
Well, that is a good question. Some of the heat is being trapped in, so not all that heat is like spreading out to all the other layers. It's kind of trapped in there, and so it's staying where, like, it never really escapes. We can't feel, like, we put our feet on the ground, we're not feeling that, right? And so you understand, like, we're not feeling that. A lot of that heat is either staying trapped in there, or some of it's transferring into the magma, which the magma is warm, and that's where that heat comes from. That's why when a volcano erupts, the magma that was inside the Earth, when it comes out and now it's lava, that lava is really hot, right? So that heat is, you know, going to some of the materials in our Earth, but not all of them. Good question. All right, and then finally, friction. So we know that more dense material are going to move down. That's just the natural process with density, right? Heavy things are going to settle. And so these heavier things are moving downward. Well, as they're moving down, they're moving past other materials. And so anything that's moving past something else is going to generate some friction. Some of that kinetic energy is going to transfer into the thermal energy as they rub past each other, okay? And that's exactly what happens. That friction, that movement, that kinetic energy of those more dense materials are going to cause that friction, and some of that kinetic energy is transferring into heat or thermal energy, and that is another one of our heat sources. And you've all done this, rubbing your hands back and forth, you feel that. So these last couple days, right, it's been pretty chilly. Next week it's gonna get even colder. And so I'm sure at some point you're gonna be like, ooh-wee, right? Rub your hands together, try to get them warm back up. Okay, and so while the Earth, so at one time it's believed that the entire Earth, and Aiden, this is kind of like going along with what you talked about, the entire Earth was this hot, melted, molten, what they call molten ball of rock, okay? And so if it was liquidy, where the more dense stuff could settle, we know that that's where, like in the center, is where the most dense material is going to end up, right? It's not going to stay at the top. If it can move downward, it's gonna do that. And that's why the core became so dense, right? Less dense at the surface by our crust. And so eventually, as the earth became more solid again and started to cool off, we got the different layers that formed. All right, so again, kind of think of that brownie example, where you have like the soft part, like in the middle, is still warmer. The outer edge starts to cool quicker, and that's what usually gets hard and crunchy with brownies. I don't know why brownies do that, and cake batter, and when you bake a cake, it doesn't really do that. But usually brownies, a lot of times, will get that hard, crunchy edge. And I always use that as kind of an example because the center of the brownie always stays pretty soft, right? The center of the pan. As you get to the outer edge, I don't know if it's just because it cools so much quicker, and that makes it kind of that hard, crunchy, and that's kind of like our Earth's crust, okay? And so we end up with kind of these different layers because they cooled off quicker, they were made of different materials, and so we get kind of the layers that we now have. It wasn't just like mixed up, right? As things started to layer and settle, and same thing kind of with my bottle. It's been a couple weeks now, and things have gotten pretty settled again. So the more dense material is at the bottom, right? And then our less dense material is all the way at the top. Pretty much just water. Still a little murky, and if we let this sit longer and longer, then obviously it's going to become more and more clear water, where those finer particles are going to settle out. But it's not all jumbled together and mixed together like it was when I was shaking it. And so the same thing kind of happened with all the different materials of this molten magma ball that was our Earth, right? As the more dense material started to settle down, it became layered, just kind of like my bottle layers, right? And so the material like the iron and nickel, which are more dense, became our core. And the less dense material like our rock became our crust, okay? And so the outer layers cooled and became solid, and the top part, our crust, as it cooled, it had big cracks that formed. It had these big cracks, and they developed because of something called thermal or heat stress, because the lithosphere is right there above the asthenosphere, and that's where all that magma and heat is. And so it caused the lithosphere to kind of crack up into big chunks. And resting on top of the lithosphere is your crust. And so the crust kind of goes with those big chunks of lithosphere. And that's what next unit's going to be all about. It's called plate tectonics. Those chunks are called plates, all right? And we'll get into that a whole lot more next unit, and I'll have a bunch of examples and things like that. But we know that a lot of this heating process is not still happening. It's still maintaining the heat that it had, and it's cooling off just a little bit every year, not much, nothing super noticeable. It's still, we figure the Earth is 4.6 billion years old. So it's not like this cooling down process of our core is going to happen overnight. It's going to be, millions of years still to come. So it's not like anything that we have to be worried about, but it does make you think, okay, like what would happen? What kind of things would be different? And it's a conversation that we'll have once we finish this unit. Like, what would be different if we didn't have the heat inside our core? What would our Earth be like now on the surface? So this is just kind of visually showing you what's going on with this. So obviously the more dense material is going to sink to the center, and the lighter material is going to kind of migrate towards the top as that dense material kind of takes the place of it, maybe. All right, and so we call this, and so as this process, this is like what they're saying the Earth was like when it was all molten and magma and melted, right? And then as it started to shift, this differentiation process happens where you get the more dense and then things kind of layered out. And then when that happened, that's kind of when this freezing started. And we're not talking like frigid, like, Antarctica freezing. Freezing is just going from a liquid to a solid. And so if you have like magma, which is kind of a liquid, becoming a solid, turning into rock, that's considered freezing, even though like for us, we're like, oh, that's not freezing, that'd be way too hot for freezing. But not everything freezes at the same temperature. So, you know, a lot of times at room temperature, something could be considered freezing. Even like a candle, if it goes from melted wax and then that wax becomes hardened again, that's technically freezing. That wax froze. It went from a liquid to the solid wax again if you're melting a candle. So we call that freezing. Sometimes that can be a little confusing just because we don't think of freezing happening at, usually we're thinking it has to be cold temperatures. All right, so here's just kind of a general kind of summary of some of the things happening inside the Earth. First of all, matter can be moving, and this could be magma, like we see here in our stenosphere, or it can be rock, which is part of our lithosphere and crust. There's also types of energies taking place inside our Earth. We have three types: thermal, radioactive, and seismic. Thermal, again, is just heat. Radioactive is that decay process where those large nuclei can't stick together and they're able to split apart and release a large amount of energy. And that's continuing to help keep our core warm. And then the next thing that we're going to talk about in this unit, which are called seismic waves, right? And so we'll get into those quite a bit. This is just kind of a nice little kind of thermometer in a way. So it's showing you how deep you're going, and this is in kilometers. And then here's the temperature in degrees Celsius, and then here are the layers. So the crust and the upper mantle, we know that's the lithosphere, right? And then we have the inner mantle, which is our mesosphere, and then we have our stenosphere, which is where our convection currents are taking place. And then we get to our outer core area, and we get to our inner core, right? And so again, just kind of showing, obviously, just like our song, as you go down, the density increases, the pressure increases, and our temperature is also increasing. And we said that that was about like 11,000 degrees Fahrenheit.
That's a lot of degrees.
It's a lot of degrees. We don't need all of that near us, for sure. Okay. So tomorrow we will we'll pick up and start into we'll start into our seismic waves tomorrow. Okay.